Hey everybody, thanks for being part of this lecture. I'm really excited to talk about this today. We're going to talk about adaptive integration, and we're going to go over how it works and go in some detail here. Now, those of you who may not be aware, integration, of course, is just the idea that we're going to mathematically figure out the area under a curve. Suppose we have a curve that looks like this. I don't know, that looks kind of like vaguely like a cubic curve. Doesn't matter. The point is, we're going to try to figure out the area right here. And you can figure that out very accurately if you know your calculus and stuff. And if you don't know your calculus, this is still a very interesting thing because this sort of math comes up all the time in engineering and all sorts of other applications that you'll use in industrial type situations. So let's get started.
Okay, so let's just start with this example. I think it's actually fairly helpful here. Now, we're going to use this function right here. You see this red curve? The red curve is represented by this function right here, which happens to be a quadratic, parabolic thing, and we're going to integrate it from 0 to 1. So this is what you see here, and this is what it would look like in that notation. 0 to 1, here's the function, dx, that's all you need to know right there. And this is what it would look like graphically. Now, of course, if we wanted to, we could just do this using the rules of calculus. The rules of calculus tell us that the integral is 4.83 repeating. So that gives us the exact answer, and there's no way we could get any more exact than that. But what if we want a computer to do this for us? Well, I think a really good way that we could start is we could say, let's have a computer do the trapezoid rule for us. Now, for those of you who are unaware, the trapezoid rule is fairly simple. It's just to say, hey, since we can't get the exact, since we can't do this math right here with a computer very easily, what if we took a trapezoid and approximated the area? Now I'm going to show you what this means. First off, here's the area of a trapezoid. You can see here it's just the average of the two heights or widths or top and bottom of this trapezoid multiplied by the height, at least in this direction. Now we're going to take this and rotate it so that the height is actually the width and the A and B are the two heights. That'll make sense in just a second here. So basically what we're doing is we're going to take the function at A, the function value at A and the function value at B, and we're going to find the average of those two, and then we're going to multiply them by the distance between A and B, that is B minus A. And we see if we do that, we get 4.75. Now, this is pretty cool. This actually gets us pretty close. It's only 17% relative error. It's not very good, but it's way closer than you might expect. So what if we want to get more accurate? Well, all we got to do is split the same area into more trapezoids. Here's how it would be represented mathematically. If you want to do this as kind of an exercise, you can actually program this in Python, and this is pretty straightforward to do. You can actually just program this exactly as you see it here, and it comes out pretty straightforwardly. Now this makes our trapezoid look like this. If I use 10 trapezoids, I'm drawing straight lines between each of these lines, and I see that I get 4.83. So that's closer. It's not exact yet, but it's much closer than 4.75. We're now down to 0.003% or something like that. I'm not doing my math exactly there, but you can see we get a lot closer. And if we could go arbitrarily high on this value n, if we say n is 100 or 1,000 or even higher, you can see that as we add more and more trapezoids, we just come closer and closer to the exact value. And you could hypothetically do that forever in the limit of n equals infinity. This would eventually reach a point where it would reach the exact 4.83 repeating. And this is what the code for Python would look for that. Although I'm leaving it to you to actually code this trapezoid rule function. So we've already established that n equals 100,000. We can get at 10 decimals of accuracy. That's amazing. But it can be really taxing on a computer, especially if we have an integral that looks like this one. Now this is just a crazy function. I think this is a really good example for what we're going to talk about today, but I'm just using this, for an example. This function is very difficult to integrate by hand, and we can't really use the trapezoid rule because it takes a lot. It takes basically 100,000 to get an even reasonable accuracy. This is what it looks like. Now, I'm going to demonstrate on the whiteboard how we might approach this if we were able.
So here's the deal. This is kind of a stiff function. It's got these tight little curves here. So obviously to get the accuracy you care about, you do need to have lots of little trapezoids. But here's the thing. This section right here and this section right here, those are basically straight lines. So what if we could just say, hey, we're just going to do one integration right there. One big trapezoid to cover all that area, and then one big trapezoid here. And then we can put in little lines in between. And we can add all those up, and it will give us a very accurate idea of the integral. And we're going to show you how that works here. Okay?
Okay. So before we move on, I just wanted to show you that I actually went through the trouble of calculating this. If we go to 10,000 trapezoids, we can get an answer, but it's extremely slow. I did one for 100, and you can see that versus the exact value, we get about 5 digits of accuracy, which is pretty good, but we're still having to do all this work when we could just do this. This is what I showed you earlier. Like, we could get one big trapezoid here, one big trapezoid here, and do a bunch of small ones where it was all tight and it made lots of curves. So we're going to go through how this could work. We're going to use a technique called recursion. Now, if you have not been able to yet, I highly recommend you go back and try to just understand recursion. Recursion is one of those magical things that we use in programming that lets us do insane things that it's sort of mind-bending, as you can kind of see from this picture here. I actually really like this picture just because it kind of explains the idea. But if you're confused about it, go look up recursion and kind of understand it generally before going on. You can pause here. Okay, let's move on. Okay, I'm going to demonstrate how to code this in Python. So we're going to define a function. We're going to call this trap_adapt, as in adaptive integration via the trapezoid method. Now, this function is going to take a few arguments. The first argument we're going to need to put in here is the function we want to integrate, so we're going to call it func. And then we're going to need the place where we want the integration to start. We're going to call it start. And we want the place where we want the integration to end. So if we jump back to the introduction, you'll remember A will be the start, B will be the end, and F will be the function we want to integrate. Okay, so the way we're going to do this is we're going to start by just making one big trapezoid from start to end. So we're going to call that a big trapezoid. Big trapezoid. Okay, so now the way we're going to calculate that is going to be function at start plus func at end divided by 2. So that'll give us the average of those 2 points. And then we're going to multiply that, give some good spacing here, by the distance between start and end, which is going to be end minus start. Okay. The second thing we're going to do now is we're going to find a midpoint between start and end. So we're just going to take the average of the two. So we're going to call the midpoint mid, and we're going to do start plus end divided by 2. Okay. Now we're going to use that midpoint to make two smaller trapezoids. So we're going to basically copy this exact same code. We're going to call this, let's say, two little trapezoids, and we're just going to do this in parentheses. Okay, you'll notice I'm using a new line character here to continue the math, and what we're going to do is instead of going from start to end, we're going to go start to mid, and we're going to go start to mid. And then on the second one, we're going to go from mid to end. Okay? Now the next thing we're going to do then is we're going to compare the area of the big trapezoid to the area of the two little trapezoids. And we're going to see if they're similar. So the way we're going to do that is we're going to say if the absolute value of big trapezoid minus two little trapezoids. Okay. If the absolute value of the difference between those two is less than some tolerance, we're going to call tol. That's actually a pretty common notation to use tol for tolerance. Then we're going to just return two little trapezoids. Okay, so this will be our base case. This is where the function ends. Basically, if the size of the big trapezoid and the size of the two little trapezoids are really close together, then we're just going to return the area of the two little ones, and that's going to give us an accurate integral. And we're actually going to define tolerance up here. We're actually going to make it an optional parameter, and we'll set it to something, the default value to something small, say 1 times 10 to the negative 5. Yeah, that's fairly small. Okay, but then if the two sizes of the two trapezoids are too big, then we're going to recurse. So the way we're going to do that is we're just going to return, and then we're going to take this exact function signature, and we're going to pass in to the tolerance value whatever tolerance was passed in here, and we're going to add it a second time. Actually, I'm going to put that on a new line here. Let's go ahead and put a new line character. There we go. And again, we're going to get rid of the default value there. And again, we're going to go from start to mid, and then from mid to end. Okay, so now that you see this, let's talk about what's happening here. So basically, if the big trapezoid and the two little trapezoids are sufficiently similar in area, we just return the two little trapezoids. Otherwise, we're going to return the recursive addition of the function from start to mid and then mid to end. So what that's going to do is for each of this, for both of these instances, it's going to go back up here and just start over again. Keep going until it hits this, and it'll keep doing this. It'll start here, go through all this, and then it'll do this check, and if they're the same, it'll go back. Otherwise, it'll return two more, and you can see how as you do this, eventually it'll recurse down to a point where where all the functions will basically, the big trapezoid and the two little trapezoids will be basically the same, and then it'll return them all together and return the sum of all of them, and what you will get is the exact integral. But using this little trick of recursion, we've made it so it can adaptively figure out how detailed to go on each part of the function. So let's take a look at what happens when we use this algorithm. So the first thing that I wanted to show you about this is that the trapezoid rule and the adaptive trapezoid rule are very similar, but you can see that you get a lot more out of a lot less. So now I'm just using the default trap adapt, and you can see that, okay, first off, the trapezoid rule with 10 iterations or 10 trapezoids gets you this far, and then using just our default tolerance, you can get pretty close to the exact answer, which is 4.83333, right? Now, you'll see that I'm using scipy.integrate.quad. We'll talk about what exactly is happening there. But the idea is that this is the exact answer. This is what our trap adapt did. And if we increase if we make the tolerance smaller, we say 1e to the negative 8 or 9 or whatever, this is just going to get closer to the exact answer. But let's see how it looks when we do that. Okay, so in this particular case, I only used 1 times 10 to the negative 2, so 1/100th is the tolerance. And you can see here that this produced 22 trapezoids. And you can see, look, it has a big chunk right here, a big chunk right here, and big chunks over here. But you can see where it needs it, it's adaptively deciding to put lots of little trapezoids in this middle region. So you can see how this is really useful, because now what we have is we have a very accurate integral, but we haven't had to make a bunch of tiny little trapezoids out of these chunks over here, which are basically straight lines. We only do it where we need it. And that is the magic of this adaptive algorithm. And you can see that with 1 times 10 to the negative 1 times 10 to the negative 2, we get about 2.5%, or excuse me, 0.25% error, and that's with 22 trapezoids. So that's a very exciting result for very little effort on our part. And we see that we have the same, same thing. Basically, this is with the hard function that we just did, the hyperbolic tangent. Same thing. You can see that we get many digits of accuracy using just our default values, versus to get the same amount of accuracy, we have to use about 10,000 trapezoids in the trapezoid rule version of this code. Okay, so the final thing that we want to do here is go back, write this code for yourself, make it work, and then say, can I optimize this code? Can I make it more efficient? Can I make it call the function it has to call? And when I say the function it has to call, can I make this the number of calls to this function? Can I minimize that for the same amount of accuracy? And so again, I've done this, I've written this version of the code basically for learning purposes, but you can take this further and try to optimize what this function does. And so I invite you to do that as part of your homework or as an assignment to you to really deepen your understanding here. Furthermore, I invite you to do the following exercises to deepen your knowledge as well. First off, we've only used one function example in this algorithm, so try using the adaptive trapezoid method to integrate various functions and notice, are there any potential problems with the method? Are there issues you may run into, and how could you solve them? So try to find an example of where this actually may give you the wrong answer. I know there are some values where you may inadvertently come to the wrong answer even though you're using the correct algorithm. Now, the second thing I want you to try is try rewriting this algorithm using Simpson's rule, and I'll provide links in the description below, but try rewriting it using Simpson's rule and say, okay, what ways is it better? Is it faster? Do we get to the answer more quickly? And compare it to the trapezoid version and kind of explain to yourself for your own understanding why using Simpson's rule might be better or worse, and try to see how you might use, why you might want to use one over the other. I think what you'll find, though, is that Simpson's rule is so much more accurate that you're going to get a better result either way. And then two more things. The thing about recursive programming is it's usually not ideal for the stability of programs. You can reach what's called the recursion depth, where you use too much memory because you have to make more versions of the function as you go down in the depth of the recursion. So see if you can write the adaptive trapezoid method without recursion. And so are there advantages or drawbacks to this? See how that works. And then finally, this is what will really deepen your understanding. Go ahead and research how these algorithms are used in production code. What I suggest is to look up adaptive quadrature and research the Python function, and that is this scipy.integrate.quad function. You can look up the source code online. But figure out how these are similar and how these are different from the ones we've programmed here, and what are the advantages and what are the disadvantages and why do we use them? Because I think what you're going to find is you're going to have very, very high quality, high accuracy integrals written in a very efficient way. Of course, a lot of these are not implemented in Python itself, but are usually implemented in C or Fortran, which are much faster and more efficient languages. So in your case, you can say, okay, what is the bare bones math that makes these tick? And I think that'll be a very important thing for you to learn and understand.
Thank you very much for being part of this lecture today. I hope this was eye-opening for some of you. I hope this was an exciting thing. I hope you can push this further and try to understand this more deeply. If you have any questions, you can put them down in the comments. I'm happy to follow up on this stuff. This is stuff I get excited about, so please just let me know. Thank you for your time, and I hope you have a lovely day.